Hello! In this video, we are going to prove the following theorem. Two distinct lines intersect in at most one point. Now, in this series, we are going to be looking at content from Edwin Moyse's book, Elementary Geometry from an Advanced Standpoint. And so, we are given a triple S, L, and P. S is a set called space, and the elements of S are what we call points. L and P are both collections of subsets of S. The elements of L are called lines, and the elements of P are called planes. Right, and from here, I'll write some of the axioms that are listed in the book in the description below. But in this video, we are going to be using the following axioms. Given any two distinct points, there is exactly one line containing them. So if P and Q are distinct points, we denote the unique line containing P and Q like this. Or we could flip the P and Q around and write it like this. Right? This is just reminding us that this is a line that contains both P and Q. And in fact, it is the only line which contains both P and Q. So this is the axiom that we're going to be using. So now, let's get into proving this theorem. To start off the proof, let's let L1 and L2 be two distinct lines. From here, we want to prove that L1 and L2 intersect in at most one point. So to prove that, let's assume for a contradiction that L1 and L2 do not intersect in at most one point. Well, then in that case, L1 and L2 must intersect in at least 2 points. So in other words, we should be able to find two distinct points, say P and Q, which both lie in the intersection of L1 and L2. But since P and Q are distinct, by this axiom, PQ is the unique line containing P and Q. Now to say that PQ is the unique line containing P and Q means that PQ is the only line which contains both P and Q. So if we are given any line which happens to contain both P and Q, that line must be line PQ. Well, we know that L1 is a line which contains both P and Q. Therefore, L1 must be precisely line PQ. And also, since L2 is a line that contains both P and Q, L2 must be precisely line PQ. So that shows that L1 and L2 are equal, which contradicts the fact that L1 and L2 are distinct. Our assumption that L1 and L2 do not intersect in at most one point led us to a contradiction. So we must instead have that L1 and L2 do intersect in at most one point. And so this completes the proof. And so yeah, that's pretty much it for this video.